Okay, welcome to a new day of trigonometry. Just going to start today with, or talk about today, it's a very short day as far as what we're doing. Going to leave quite a bit of practice with our unit circle so that we can get hopefully to the point that we are not quite as reliant on looking up all of these values that we need for our trig functions. So as you go through the problems today, do your best to kind of set that unit circle to the side, come back to it as you need it, but try to recall the values as best you can, excuse me, as best you can before you look them up. And of course look them up to justify or to verify that you're correct, but we're trying to wean ourselves off of that, as that is not something we want to have to recreate each time or need in order to evaluate our trig functions at our special angles. So anyhow, today we are going to discuss identities, and I already have the identities we've come across so far listed here. Just going to run through them again, labeled by where they come from. First off, our reciprocal identities, sine and cosecant are reciprocals of one another. So sine is 1 over cosecant, cosecant is 1 over sine, just indicating that they are reciprocals of one another. Same as cosine and secant, also a reciprocal pair, and tangent and cotangent, also a reciprocal pair. Things that I believe we talked about those last Thursday, if I'm not mistaken. But regardless, reciprocal identities here again hold true. Additionally, we have the quotient identities, and these I don't think we've written down kind of as in this manner thus far, but as we went through our circle investigation, we found that tangent was our y value over x value. So in order to evaluate tangent from our unit circle, we would find the y value at the coordinate, put it over the x value at the coordinate, and we'd have our tangent. Well, since the y value was sine and the x value is cosine, essentially what we are doing anytime we put y over x is we're putting the sine over the cosine. Thus, sine over cosine is tangent. Well, since tangent and cotangent are reciprocals of one another, sine over cosine, the reciprocal of that would be cosine over sine, thus that is cotangent. And those are our quotient identities. So far no identities we haven't come across already, written a little differently than we've become accustomed to here, but same idea. So we're going to come back to this page and include our Pythagorean identities. I'm going to spell that wrong. I have to look at it. There it is. So the next identities we're going to look at is are our Pythagorean identities. And I'm going to pull away from this page so I can have a complete note sheet here when we're done. We'll come back to it in one moment. But first I'd like to look at the idea of where these identities come from. Somebody really smart a long time ago decided that the Pythagorean theorem applied to trigonometry. Pythagorean theorem and trigonometry are based on the same idea. They're both based on a right triangle. Trigonometry based on the relationship involving an angle. We'll call the angle theta, as we have been most often. And specifically sides. So we're going to put this in old school Pythagorean theorem form. We're going to call this side A, this side B. Those are the legs of a right triangle, making the hypotenuse C. And if we start with the Pythagorean theorem, we know that A squared plus B squared equals C squared. Nothing new here, nothing earth-shattering, just a relationship between, or the relationship between the lengths of the sides of the two legs and the hypotenuse of a right triangle, found by Pythagoras, called the Pythagorean theorem. Okay, well this is an equation, and as we know, we can do anything we want to an equation. So what we're going to do here is I'm actually going to just do a little bit of algebra to this before we bring in this idea of trigonometry. So if I divide both sides by c squared, first and foremost I'm dividing two sides of an equation by the same value. Provided that value is not 0, I'm always allowed to do that. Well, c is a length of a hypotenuse. Well, no triangle has a hypotenuse of length 0, therefore I can divide by c, or in this case c squared. Well, dividing on the left side here I can rewrite as a squared over c squared and b squared over c squared. And on the right hand side, anything divided by itself is always 1. Well, my exponent rules say that if I have a numerator and denominator to the same power, I can rewrite that as a over c squared plus b over c all squared equaling 1. And this is where the jump from the Pythagorean theorem, as we started with, becomes a trigonometric expression. Let's look at these ratios a over c and b over c in relation to this triangle we started with. So when we began, I gave this angle theta a name. This angle theta is this acute angle in this right triangle. Well, let's look at where A, B, and C are. Well, in relation to theta, A is the adjacent, B is the opposite, and C is the hypotenuse. Well, that means that A over C is what ratio of this right triangle based on this angle? Bump, 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 bump. Yep, that's right. It is this. No, it's not. That's wrong. It is the cosine of theta, because the cosine of an angle is the adjacent over the hypotenuse, so A over C is the cosine. Similarly, opposite is B, hypotenuse is C, so the sine of theta is B over C. So bringing that idea back to this equation we created using the lengths of these sides, A over C squared is actually cosine of theta squared. B over C squared is actually sine of theta squared. And this brings us to our first trigonometric, Pythagorean identity, that sine squared theta, and this is how we write sine squared with the power between our angle and our sine function. Sine squared theta, meaning sine of theta all squared, plus cosine squared theta equals 1. Now, this is my first Pythagorean identity. It is a relationship between sine and cosine, that if you have sine squared plus cosine squared, it always equals 1. Meaning, if we are in a situation where we have sine squared or the sum of sine squared and cosine squared, we can simplify it to become just 1, which is very, very often quite useful. So this is our first Pythagorean identity. We'll come back to that in just a second. What we're going to do is there's actually two more, and I'm going to start with the first, and there are multiple ways to get to the next two, but I like to just go straight from the trig. If I start with this, again, I can divide by anything I want. So what I'm going to do is I'm going to divide everything by sine squared theta. Okay? Well, dividing by sine squared theta, sine squared divided by sine squared is 1. Cosine squared over sine squared, well, cosine over sine is cotangent, so this gives me cotangent squared theta. And 1 over sine squared is cosecant squared theta. And this is our second of our Pythagorean identities. The third is created by taking sine squared theta and cosine squared theta, and sine squared plus cosine squared theta equal to 1. And instead of dividing by sine squared, we must divide by cosine squared. Please pause the video, take a moment, and do it. Okay, here we go. Just kidding, you didn't pause it. Alright, now here we go. Pause it and do it. And done. Alright. Now we'll divide by cosine squared. Sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine squared, 1 over cosine is secant, so this is secant squared theta. And these three make up our Pythagorean identities. Let's go ahead and put them on our handy-dandy note sheet, and we'll have all of our identities on one nice form for our reference. So our Pythagorean identities are sine squared theta plus cosine squared theta equaling 1. 1 plus cotangent squared theta equaling cosecant squared theta, and tangent squared theta plus 1 equals secant squared theta. And we can use those in quite a few applications. This afternoon, or right now, in the page 307 section, numbers, let me just look at it real quick, numbers 37 to 43 use these identities and apply them to the situation at hand. So let's go ahead and look at one together. Let's look at number 44 on page 307. we are given the instructions to use a trigonometric identity to transform the left side of the equation into the right side of the equation. And on number 44, we are given that sine squared theta minus cosine squared theta equals 2 sine squared theta minus 1. Okay. Well, what we're going to do to make this happen is we're going to start as instructed with the left-hand side of this equation, and we're going to manipulate it until we find the right-hand side as our result. So, notation for manipulation means each thing we write has to be equal to the previous statement. So I'm going to start with sine squared theta minus cosine squared theta. I can see here I want to change everything to sine, so I'm going to try to change cosine squared theta into some expression of sine. So I'm going to use this Pythagorean theorem involving sine squared and cosine squared. Excuse me. And I need to rewrite it. So I'm going to start with sine squared plus cosine squared equals 1. I'm just going to do this over up to the side. So I have sine squared theta plus cosine squared theta equals 1. And in this equation, I have a cosine squared theta. Let me grab a pen that actually writes. Here is cosine squared theta, and I'm going to isolate it. So if I subtract sine squared over, I have that cosine squared theta equals 1 minus sine squared theta. So what I can do now is I can take this expression and replace it for cosine squared theta. Replacing that, I have sine squared theta minus 1 minus sine squared theta. Okay? Well, that will equal, distributing the negative, sine squared theta minus 1 plus sine squared theta. And combining my like terms here, I have 1 sine squared theta and another, giving me 2 sine squared theta minus 1. And I've used that Pythagorean identity to change sine squared minus cosine squared theta into 2 sine squared theta minus 1. Began with the left side, step by step, until I ended with the right side. Okay, questions? Just kidding. Give it a shot. Here's your assignment for the evening. Page, what is it? Let me see. Page 297. 10 through 46 even. These are more unit circle practice as we're trying to get our unit circle values, or our trig ratios from the unit circle, internalized. So please work through those. They're the same steps, same processes as yesterday. We are just looking to determine those unit circle, or develop our unit circle skills so that we can get away from having to use that unit circle each time as a reference to evaluate a trig ratio at a given function, or at a given angle. So the 297 is review from the other day, the things we need to work on internalizing, and the 307 set here uses those identities along with some other pieces to get us where we want to go. Alrighty, enjoy.